So now Arthur-César le Bras will continue the lecture series on p-adic geometry with BanachColmez spaces.
Yeah, thank you very much. Okay, so let me recall briefly what we did last time. So we fixed a finite extension E of QP, and we saw that to any, so with uniformizer pi, and residue field FQ, and to any perfectoid space in characteristic P, living over FQ, we can attach a Farc Fontaine curve, which also implicitly in the notation depends on E. And so we are interested in vector bundles on this curve, I mean on this adic space over spa E. And basically we saw two things on Tuesday. So first thing was that there exists a natural tensor functor from the category of isocrystals over K, where K, I recall, is just the algebraic closure of FQ, to the category of vector bundle on the Farc Fontaine curve for any such S. And this category we understand very well because it's semi-simple with simple objects indexed by rational numbers. And then we studied cohomology of these objects, and we saw that for any lambda in Q, the structure map from BC of O lambda to the point, which is just spa D of Q, the V sheaf associated to spa FQ. This map is representable in locally spatial diamonds. So diamonds whose underlying topological space look like the underlying topological space of an analytic adic space, and is also partially proper. And the definition of this object, of this diamond, depends on the sign of lambda. So it's a relative H naught if lambda is non-negative, and it's a relative H1 if lambda is negative. And in both cases, the other possible cohomology just vanishes, at least pro-étale locally. Okay, and I mean, I use this notation without really explaining it. So of course, like BC stands for BanachColmez. And so Colmez originally defined a category of objects with like a different name, and later they were called BanachColmez spaces, and he proved that they form an abelian category. But this definition was given before the Farc Fontaine curve was discovered. And so now I somehow take the opposite perspective of defining this kind of objects from vector bundles on the Farc Fontaine curve. Okay, and let me just also briefly recall a few examples. So we saw that BanachColmez space of O1 corresponds to spa D of perfectoid formal power series ring in one variable over FQ. We also saw that the BanachColmez space of the structure sheaf is simply given by E underline. So here, so here you see that I mean, even if we think to this Farc Fontaine curve XS as some kind of family of Farc Fontaine curves indexed by parameterized by S, you see that the behavior is really different from what would happen for a classical curve in algebraic geometry, so a complete one, like P1, for example, because if you just look at relative H naught, you would just get something like represented by the affine line, something like GA. But here you rather get just E underline, a locally profinite set. So that's an instance of the difference between this relative Fark-Fontaine curve and usual family of algebraic curves. Well, it's just what I explained last time. So to S in perf FQ, you just attach, well, if the vector, like, that's what you do when lambda is non-negative, and otherwise you take the Schiffification of this functor with H1 instead of H naught. And the last example we discussed was the example of BanachColmez space of O-1. And for this one, to give an explicit presentation, contrary to these two cases, I somehow need to first fix a perfectoid base. So if we fix S in perf FQ together with an untilt S sharp leaving over E, and then we can explicitly describe this one as the diamond of the affine line over S sharp divided by the action of E underline. Sorry, and once again, I forgot to base change it to S. So it's as a functor on the category of perfectoid space is leaving over S. Okay. So the first thing I want to do today is to discuss the situation of our geometric point. So because, I mean, we have this functor, but we would like to know more about its properties. So this is something which is understood over a geometric point. So I will take C to be complete, algebraically closed, perfectoid field over FQ. And so I will consider the Fark-Fontaine curve for spa C. So let me just denote it by XC. So this is the first case that was studied by Fark and Fontaine, and in this case, I prove the following theorem. Is that the functor we have from isocrystals over K to Ben XC is actually essentially surjective. Which, because we know what this category looks like, we can rephrase by saying that any vector bundle E on XC can be written as a finite direct sum of all lambdas with lambda in Q. Okay, but I should directly point out that this functor is far from being fully faithful, even in this particular case. So in the category of isocrystals, you don't have morphisms between objects of different slopes. So if you look at the, say, for example, the isocrystal of simple isocrystal of slope 0 and the one of slope -1, there are no morphisms between them. But morphism in the category of vector bundles on the curve between the structure shift and OXC of 1, it will be, well, the C point of what we call BC of O1, and this is huge. This is an infinite dimensional E vector space. So this is a space, the eigenspace for the eigenvalue pi of Frobenius on the space of all rigid analytic functions on Y. And so this is very big. Okay. So I want to try to sketch a proof of this result, which is not the original proof of Farc-Fontaine, but which is due to Farc-Scholze. I mean, it's only a sketch. Because in this proof, we will make use of the geometry, I mean, of the properties of these diamonds, of these BanachColmez spaces. So the proof I somehow decompose it in 3 steps. The first step, I don't want really to say anything about it. It's the case of line bundles. So in this case, well, you prove that they are just indexed by the degree. So you prove that the map sending an integer n to the line bundle O of n is a bijection. And well, this is a part of the proof where you still need to use the schematic Farc-Fontaine curve, which I did not discuss, and some properties of the ring of functions on this schematic curve when you remove a point. So the fact that it is a principal ideal domain. So I just want to take this for granted and not say anything about this part. Then there is a series of reductions that you have to do. So I'll try to briefly summarize them. So the first observation is that if you have a vector bundle on XC, we can now make sense of, because of step 1, we can now make sense of its degree. Namely, we just define the degree of E to be the degree of the determinant of E, so the top exterior power of E, which is a line bundle. And here on the right-hand side, the degree is understood as the inverse of this bijection. And then you can make sense of the slope of a vector bundle. To be the quotient of the degree of E by its rank. And you check that this slope function satisfies the axiom of the Hardor-Narasimhan formalism. And so from this, you deduce that any vector bundle E on the Farc-Fontaine curve XC has an exhaustive Q-indexed filtration. Indexed by rational numbers, by sub-bundles, in such a way that for any lambda in Q, if you look at the quotient of the lambda filtered piece by, well, the union of all pieces corresponding to indices lambda prime bigger than lambda, then this is, well, let's see, call this E lambda, then this is semi-stable of slope lambda. So semi-stable, I recall, just means that a vector bundle is say to be semi-stable of slope lambda whenever if you have a subbundle, then its slope is necessarily less or equal to lambda. Where, sorry? Okay. Yeah, formalism. And this stands for Arthur-Narasimhan. And one checks that this Arthur-Narasimhan filtration is somehow compatible with change of the base field E and change of C in some appropriate sense. Well, changing C means just like I could replace C by a bigger perfectoid algebraically closed extension. Okay. So the proof of the theorem is now by induction on N. So the case where N is 1, I already assumed it. So it is the content of step 1. And so now let N bigger than 1 such that the theorem holds for all when the rank is less than N. Okay, so we see that if E is not semi-stable, so let me take a vector bundle of rank N on XC. Then if E is not semi-stable, of some slope, then we are down by the inductive hypothesis and the fact that H1 XC of O lambda vanishes whenever lambda is positive. Right, so if the vector bundle is not semi-stable, the Arthur-Narasimhan filtration is non-trivial. So I can take the first piece and its quotient. They have different slopes. To both of them, I can apply my inductive hypothesis. And then the extension between them must split because of this vanishing of H1. So we can assume that E is semi-stable of some slope lambda. And let me write lambda as D over R, where, as usual, D and R are co-prime, and R is assumed to be positive. Oh, sorry. Right, okay. So now let me assume that I have a map which is non-zero. From O lambda to E. So what we know is that the category of vector bundles, which are semi-stable of slope lambda, is abelian, and the simple objects are given by the stable vector bundle. So if this means that, because E is also semi-stable of slope lambda by assumption, this means that, first of all, this one is simple in this category. So this map will automatically be injective, and then its co-kernel will also be a vector bundle semi-stable of slope lambda. But then I can just again apply induction hypothesis and the vanishing on H1 to deduce that, in fact, so again, induction plus H1 of XCO being trivial implies that if I can do that, I will deduce that E is isomorphic to a sum of copy of O lambda. Okay, and one further reduction, so we see that really what we have to produce is a non-zero such map. And no, just by changing, well, like increasing E will just, like if I push forward from the Fark-Fontaine curve for E prime to the Fark-Fontaine curve for E, where E prime is a finite extension of E, this just amounts of like keeping the same degree and increasing the rank. So I can also up to changing E, assume that in fact lambda is in Z, and then by twisting, even assume that lambda is 0. Okay, so this is the setup we have reduced to. We have a semi-stable vector bundle of slope 0, and we want to produce a non-zero global section. What do you mean by the part of lambda? The first argument, you mean? Sorry, I did not quite understand. Okay, so that's one, so to say, first reduction. Then the next reduction is to observe that we are also free to increase C, i.e. to replace C by some bigger perfectoid algebraically closed extension of FQ. Indeed, if we can find a non-zero global section of our vector bundle E on XC after base change to XC prime, where C prime is, as I said, also complete algebraically closed extension of C, then this means that the sheaf sending S perfectoid space over C to isomorphisms between the structure sheaf, I mean, n copies of the structure sheaf and XS. This will be a torsor because it has, I mean, if by the same argument, if I can produce a non-zero global section, by induction, I can actually produce a trivialization of E. So if I assume I have a C prime point, then this is GLN E V torsor. Just because if I have one isomorphism, then all the other isomorphisms will just be obtained by precomposing by an automorphism of this vector bundle. But we've seen that the global section, the sheaf of endomorphism of the structure sheaf is just E underline. So when you do it for the n-dimensional one and you look only at automorphism, you exactly get this structure group. But then it's actually automatically represented by perfectoid space, which is poetal over space C, and thus has a section. So here I'm hiding the fact that because this group is locally profinite, I can just, like, if I just mod out by some compact open subgroup and let this compact open subgroup go to the, like, shrink to 1, I can present this this torsor as an inverse limit of things which are like locally for the V topology étal over my base. And also in étal cohomology of diamonds proves that you have V descent for étal morphisms. So in fact, you can really represent this by a perfectoid space over space C. Okay, so that's one further reduction one can do. And so finally, let's pick D, which is non-negative and assumed to be minimal with the properties that we have an injective map from O minus D to E. So our goal is to prove that we can to prove that D is actually 0. I mean, here we have line bundle, so injective and non-zero is the same thing. And note that this is actually, it's not completely obvious that this is actually well-defined, this integer D. But one way to see it is to use the fact that, in fact, O1 by some results of KDLU is ample. So after twisting E by O of 1 like sufficiently many times, it's actually even globally generated. So I certainly do have non-zero such maps. This property is in fact also used in step 1, which I did not discuss. Okay, and then there are some further small reductions which I skip. Well, first what you can observe is that D being minimal, it forces the quotient, like the co-kernel of this map, to be in fact also a vector bundle. I mean, it may a priori have some torsion, but if you replace by the saturation, then you get something with, you would get something which contradicts the minimality, like still injective and contradicting the minimality of D. And what you can also reduce is, so let me just try key case to which you reduce is a case where D is in fact 1 and F is semi-stable. I mean, that's, both assumptions are not necessarily satisfied, but there is a way to reduce to these two conditions. And so in fact, then F must be, because E is of degree 0, rank n degree 0, this is rank 1 degree -1, so necessarily F by the induction hypothesis will be isomorphic to this one. Yeah, I was. Yeah, I was good. Yeah. So I was going to. Yeah, I wanted. Yeah, okay. So that's what I wanted to come to. So this step 2 is not really new in the Farc-Schulze argument, as Peter just pointed out, it's present in all known proofs, like this proof of Kedlaya, the one of Hartle-Pink in positive characteristic, or also in the proof of Farc-Fontaine. And so now we reduce to the key statement, which I will just rewrite, which is the following proposition, that imagine if we have an extension of, so now I rename n-1 to be n. So let's have such an extension of vector bundles on XC for some positive integer n. Then we claim that there exists C prime over C, an extension which is again complete algebraically closed perfectoid field with the property that we have our desired global section. And so this will, by the reductions I sketched, this will conclude the argument. And so this is where the proof of Farc also differs from the previous proofs. So let me get the statement. So assume not. Let's try to argue by contradiction. So then what do we have? When we take cohomology of this short exact sequence, by assumption, for any perfectoid field extension, that's algebraically closed of C, H0 of this one vanishes. So we get an injection of V shifts between the BanachColmez space of, so the diamond attached to O1 over n, and the BanachColmez space of O-1. So here I'm implicitly using that I have a morphism. So these are both locally spatial diamonds by what we've already seen. I mean, to be strictly speaking, I should write like C as an index, because now they are seen as objects, as sheaves on the category of perfectoid spaces over C. And to check that the morphism between locally spatial diamonds is injective, it's enough to check on geometric points. And this is exactly what our assumptions give us, that this map is injective. Okay, but now we, by the work of last time, we know what these objects look like. Here the slope is strictly between 0 and 1. So we know that this is represented by, like, absolutely, it's, as I said, it's p-adic of a formal power series ring. But so after you base change to this perfectoid field C, it gets represented by the perfectoid open unit disk. Okay, and so in particular, it's connected. And what is this? Well, let me pick some untilt, C sharp of C. And then, as I recall, it's just given by that. So the first claim about this map, so okay, we know it's injective. I also claim that the image of this map, so let's call it F, cannot be contained in classical points. And by classical points, I mean that on A1, like the underlying topological space of this diamond is the same as the one of the usual adic space. And so we have like classification of the points. And the type 1 points are the classical points. And I claim that the image cannot be contained, of F cannot be contained just in this set of points. And the reason is that this is, well, this is a totally disconnected set. But this map on the topological space is continuous, and this is connected. So it could not be injective if it would factor through these classical points. So also up to increasing C, I mean, I can also ensure that the field C is spherically complete and has value group given by R cross. So I can actually just assume that all non-classical points are type 2 points. So we therefore deduce that the image of F must contain a type 2 point. So corresponding to a Gauss norm on some disk inside the affine line. And now the observation is that we have this freedom of increasing C. So the observation now is that if I pick the pre-image of this point, so let's call it X, in the p-adic affine line, but no, not over C anymore, but let me pick the residue field at this point and, well, take the completed algebraic closure of this field. It contains, so now after this pullback, these points become a classical point. And in fact, the image contains an open disk around, well, yeah, around the classical point. I mean, as I said, this type 2 point correspond to a Gauss norm on some disk of radius A and, sorry, of center A and radius R. And after pull back to this bigger algebraically closed field, I claim that the inverse image of this point contains all the open disk of the same radius around its pre-image. So in particular, this tells me that, in fact, the image of F, because it's also a group morphism, so it must contain an open neighborhood of 0. But then on A1, everything is, my target is not A1 itself, but it's quotient by the action of E. On the morphism I have is E linear. So I can use the scaling action by E cross to in fact show that if the image contains a neighborhood of 0, it has to, by scaling by powers of the uniformizer pi, it has to contain, it has to be actually surjective. Okay. And so finally, we conclude that, in fact, our map F must be an isomorphism of these shapes. And now we have the desired contradiction. So let me write it. Why is it a contradiction? Well, now we can again look at both sides. The source is a perfectoid space. So in particular, if this is an isomorphism, this means that A1 would also be a perfectoid space over C. But so A1 is a proetal E torsor over this quotient. And so A1 itself would be a perfectoid space. okay, which is not true. So, okay, here to simplify a bit the end of the proof, I'm really using that we have assumed from the start that our field was p-adic field. The same argument, you would need to argue a little bit more to deduce the same, to get the same a contradiction in the case where E is positive characteristic. Because in positive characteristic, you can't really distinguish between a space and its perfection as a functor on perfectoid spaces. But even in this case, you can actually get a contradiction. Okay. So, okay, sorry, I said it orally without writing. So the image contains some neighborhood of 0, but the map is E-linear. So I can always scale this neighborhood of 0 by a power of pi, and that will still be in the image. And so then I can cover all of A1. Okay, so let me add 2 remarks about this statement. First remark is that from this classification theorem, you can, as observed by Farc-Fontaine, you can deduce that the Farc-Fontaine curve is geometrically simply connected. So it lives over spa E, but after base change to completed algebraic closure of E, it has no non-trivial finite étal covers. This is something you can deduce from the classification theorem, and the same argument would also work with P1 if you use a Grothendieck classification of vector bundles on P1. And the hint is to, if you have some finite étal OXC algebra, the trick is just to try to see it as a vector bundle, use a classification theorem, and then remember the extra structure, the multiplication law you have on it, the algebra structure together with a trace pairing to, in fact, deduce it must be semi-stable of slope 0 and therefore comes from a finite étal algebra over E. So that's one nice application of this classification theorem. Maybe another remark I can make is that to come back briefly to the discussion about p-divisible groups, that, I mean, we saw it a little bit last Tuesday in the case of O of 1. So let me just assume that E is QP for simplicity. And let H over K be a p-divisible group. And D, it's a Dieudonné module. So this is an isocrystal. So in particular, I can attach to it a vector bundle, ED. So, well, okay. On XC. So here C is, yeah, as before, a complete algebraically closed field in characteristic P. So there are various normalizations for the Dieudonné module. I want to pick one such that this has slopes between 0 and 1. And imagine that we have some untilt C sharp of C, like living in characteristic 0, and G, which is a p-divisible group over the ring of integers of C sharp, whose reduction mode P is isomorphic to, well, to the base change of H to OC mod, OC sharp mod P. Then we can perform the following construction. So we can, so our untilt C#, first of all, it gives rise to a Cartier divisor on the curve. Let me call I this closed immersion. And then we can map E to, well, so to say its restriction along this, this point. So this has an explicit description because we know what the completed local ring of the Fark-Fontaine curve at this point look like. And so we just get D times a certain paired ring, B plus the RAM attached to our untilt. And the choice of G, the lift of our P divisible group H, gives, by say Grothendieck messing theory, it gives us Hodge filtration on D, which I mean on D tensor C. So first I can I'm not done yet. No, I want to apply the theta map. Yes, okay, yeah, sorry, because okay. So let me write C directly. That's even more simple. You're right. Yeah. Over QP breve. And now I have the Hodge filtration, which is given by the Lie algebra of G, which I base change from OC# to C#. Okay, and these maps are surjective. And so, well, let me look at the composite map, I don't know, F of G. So this is like a skyscraper sheaf supported at this point of the Fark-Fontaine curve corresponding to our given untilt. And I can denote now by E of G the kernel of this map. And now the p-adic comparison theorem in the case of P divisible groups tell us that in fact this vector bundle EG is semi-stable of slope 0, and it identifies with the Tate module of rational Tate module of G times the structure sheaf on the Fark-Fontaine curve. So in particular, we see that all modifications of the vector bundle attached to the isocrystal D, which arise from P divisible groups over the untilt, well, which lift H, are, as vector bundles, they are semi-stable of slope 0. I mean, they are trivial. But how many ways you have to modify to do a degree? Well, let's say, for example, you now take H to be dimension 1 on height n. So now this Lie algebra is one-dimensional, so you are doing a degree 1 modification of this vector bundle E. And so doing such a modification is just like choosing a line in the fiber at infinity. So the set of modification will identify with projective space of dimension n minus 1. And so what we are basically saying here is that for all, so have a map from a set of p-divisible groups over OC sharp, lifting H to Pn1 minus 1 of C sharp, just given by looking at this Lie algebra inside the fiber at infinity. And what we deduce from these considerations is that if we know that this map is surjective, we conclude that any degree 1 modification of E, which because of the assumption on H is just a vector bundle O1 over N at the point corresponding to C sharp, is trivial. And in fact, this is known to be true in this situation because this map is not just a not a map of sets. There is actually a map of p-adic spaces. This is a well, more or less Lubin-Tate space, and this map is a paired map, the Gross-Hopkins paired map. And we know by work of Gross-Hopkins and Lafay that this map is in fact surjective. So you see that this statement about paired morphisms for moduli spaces of p-divisible groups gives you some information about the type of modification of these vector bundles that you can make at infinity, I mean, at the point corresponding to your untilt. And the original proof of Farc-Fontaine was using this observation instead of this argument that we did in step 3. So the advantage of this new argument is that the proof is in some sense much more direct, but this argument has a nice feature that it shows in a very special situation how modification of vector bundles on the Farc-Fontaine curve are related to, well, moduli spaces of p-divisible groups. Also, that was a very sketchy explanation, but okay, so I started at 15, so I think I have 10 minutes left. Let me try to say something about families of vector bundles. So now we have some understanding of what happens over a geometric point. And in chapter 2 of Farc-Scholze, you will see also many statements about families of vector bundles. So families means just that I'm looking at vector bundles on the Farc-Fontaine curve XS for some perfectoid space S, which is not a geometric point. I don't have much time left, so let me just focus on one specific statement and try, because once again, this will be a statement about vector bundles that we will prove using the geometry of Banach-Kolmez spaces. So let me state first the result about BC spaces. Okay, so we pick a perfectoid space over FQ. And now we also pick a vector bundle E on XS. But we do not assume that it comes from an isocrystal, so we a priori don't know much about it. And then the claim is that BC of E, which I define to be again the functor on the category of perfectoid spaces over S, mapping T to H0 of on the Farc-Fontaine curve for T of E. I claim that, okay, first of all, is as before locally spatial and partially proper diamond over S. But even better than that, if I remove the zero section, so it means that I only look at global sections which are non-zero fiber-wise on T, and I model by the natural action by E underline cross on this, then this is now again locally spatial diamond, but this is even proper now, instead of just being partially proper over S. Okay, so I think my notations are a bit contradicting themselves because, yeah, okay, before when I had a vector bundle coming from an isocrystal of negative slopes, I defined BC to be the relative H1, but now I'm somehow switching notation. Well, yeah, I know. Okay, yeah. Anyway, so one very brief word about the proof of this. So how do you control an arbitrary vector bundle on XS? Well, for the first part of the statement, the key point is, again, the ampleness of O1, which is true. So, I mean, it's a local statement on S. So we can assume that S is affinoid perfectoid. And in this case, by a result of K-dial U that I already mentioned, but no over a more general base, O1 is ample. So this means that by applying this to the dual of E, I can get a surjective map from O minus n of M to E for some integer n and m, sorry, to E dual. And so by dualizing, I deduce that I have a short exact sequence like this, where F is again a vector bundle because it's the dual of the kernel of this map, which is a vector bundle. And so we see that because of this, this implies that our V sheaf BCE is in fact a closed sub V sheaf of the BC space of O and M. But now this one we already know because we understand what happens for vector bundles coming from isocrystals. We know that this one has all the required properties, so it's locally spatial diamond, it's partially proper. And well, no, this nice property of diamonds that a closed subsheaf of a locally spatial diamond is still a locally spatial diamond and partially proper as well. So that's about step one. Step two is more complicated. So for step two, I mean, for the second part, well, observe that we will already know that. So what does that mean to be proper? Proper is partially proper plus quasi-compact. And so here, all we are left to check is that this object is in fact quasi-compact. So the situation is kind of opposite for diamonds to what it is usually for schemes, where for schemes, usually if you want to prove that something is proper, the real difficulty is proving that the variative criterion of properness is satisfied. QCQS assumption is usually not problematic. And here it's kind of the opposite. The difficult part is really the topological part, that this is in fact quasi-compact. And this is like really a topological argument, somehow using that if you have a topological space T, which looks like the underlying topological space of an analytic p-adic space. So this will be satisfied by, in our case, by what we already know from the first part. And you have some automorphism alpha of this topological space such that the fixed point of alpha, which is a subspace of T, is spectral. so in particular quasi-compact, and such that somehow, okay, I don't want to write the full statement. You also impose that the action of, if you let positive powers of alpha act on any element of T, and you look at you let this positive power go to infinity, anything will converge to this fixed point locus. But you also want the opposite property when you look at negative powers of this automorphism acting, you want that this really diverges away from this fixed point locus. And then the conclusion is that in this situation, when you remove this fixed point locus from T and you model it by, well, the action of alpha, powers of alpha, then this is spectral. So in particular, quasi-compact. So here you apply this to T being the underlying topological space of this diamond, BCE. The zero section is your T0, and the action is just the action of the uniformizer pi in E cross. So because you assume that S is affinoid perfectoid, this assumption about the fixed point locus is satisfied and so on. Okay, so let me just take 1 minute to state the application. So this application will tell us that if I take a vector bundle on a relative Arc-Fontaine curve, if I assume that its Ardan-Arasiman polygon is constant when the point on S varies, then I can actually, up to a Proetal cover, I can actually also write it as a sum of vector bundles coming from isocrystals. So let me write the theorem. So it's originally due to Kedlaya-Liu, but the proof I explained now is also due to Fark-Scholze. Assume that the Ardan-Arasiman polygon of E is constant. So what I mean by this is for any geometric point of S, I can look at the restriction of E on the Fark-Fontaine curve corresponding to this point. And by the classification theorem, I know that it is a sum of O lambda, so I can write its Ardan-Arasiman polygon. And I want to assume that it does not vary when the point of S varies. And then what we deduce is that there exists a global Ardan-Arasiman filtration on E, which splits Proetal locally on S. So up to replacing S by a Proetal cover, my E is a sum of vector bundles which are fiber-wise semi-stable of slope lambda for various lambda. And I can also, up to taking a further Proetal cover, trivialize each of these pieces. So I can really have a nice, I can write my vector bundle as a sum of O lambda locally on S. And okay, let me just say what the main idea is. So the key claim is you take lambda to be, okay, so the polygon is, Ardan-Arasiman polygon is assumed to be constant, so it makes sense to speak about the maximal slope of E. And the key is to produce, to show that V locally on S, there exists a map from O lambda to E, which is fiber-wise non-zero. If you can do that, then you can somehow argue by induction and prove the statement. But the key is really this. And equivalently, this is the same as saying that you have a non-zero map, fiber-wise non-zero map from the structure sheaf to F, which is the internal home from O lambda to E. Right? That's just tautological reformulation. But now we observe that the BanachColmez space of F minus 0 is, well, will map to S. And I claim that this is precisely the V cover over which we have such a section. Right? I mean, this last part is more or less by definition of this BC space. What is not so clear a priori is that this is a V cover. But the reason it's a V cover is that I can factor it as VCF minus 0 modulo E cross mapping to S. And this we know to be a proetal torsor by definition, proetal E cross torsor. And now this one, by the proposition, the map is proper. So in fact, all we care about is that the map is quasi-compact. So it's a quasi-compact map of V sheaves, which is also surjective on geometric points. Because on geometric points, we have the classification theorem, which tells us that we have such a non-zero section. And this implies, again, by some topological arguments with using the specific properties of analytic adic spaces, then this map is actually surjective. So it's a surjective map of V sheaves. And so this is indeed the desired V cover, let's say S prime, over which I have my non-zero section. Okay, sorry for going over time. I will stop here.